Metamaterials are artificial materials engineered to have properties that have not yet been found in nature. They are assemblies of multiple individual elements fashioned from conventional materials such as metals or plastics, but the materials are usually constructed into repeating patterns, often with microscopic structures. Metamaterials derive their properties not from the compositional properties of the base materials, but from their exactingly designed structures. Their precise shape, geometry, size, orientation and arrangement can affect waves of light or sound in a manner not observed in natural materials. These metamaterials achieve desired effects by incorporating structural elements of sub-wavelength sizes, that is, features that are actually smaller than the wavelength of the waves they affect. The primary research in metamaterials investigates materials that are able to reverse the refractive index. These materials, known as negative index metamaterials, additionally permit the creation of superlenses that can greatly increase optical resolution beyond the capability of conventional lenses, becoming a solution to the centuries-old problem of diffraction-limited systems. In other work, a form of invisibility has been demonstrated at least over a narrow wave band with gradient index materials. Although the first metamaterials were electromagnetic, acoustic and seismic metamaterials are also areas of active research. Potential applications of metamaterials are diverse and include remote aerospace applications, sensor detection and infrastructure monitoring, smart solar power management, public safety, radomes, high-frequency battlefield communication and lenses for high-gain antennas, improving ultrasonic sensors, and even shielding structures from earthquakes. The research in metamaterials is interdisciplinary and involves such fields as electrical engineering, electromagnetics, classical optics, solid-state physics, microwave and antenna engineering, optoelectronics, material sciences, nanoscience, semiconductor engineering, and others. History. The history of metamaterials is essentially a history of developing certain types of manufactured materials, which interact at radio frequency, microwave and later, optical frequencies. Seminal explorations of artificial materials for manipulating electromagnetic waves at the end of the 19th century. Some of the earliest structures that may be considered metamaterials date back to Jagadish Chandra Bose, who in 1898 researched substances with chiral properties. Carl Ferdinand Lindemann studied wave interaction with metallic helices as artificial chiral media in the early 20th century. In the 1950s and 1960s, artificial dielectrics was studied for lightweight microwave antennas. Microwave radar absorbers moved into the research arena in the 1980s and 1990s as applications for artificial chiral media. Winston E. Koch developed materials that had similar characteristics to metamaterials in the late 1940s. Materials that exhibited reversed physical characteristics were first described theoretically by Victor Vesligo in 1967. He proved that substances with a negative index can transmit light. In such a material, he showed that the phase velocity would be anti-parallel to the direction of pointing vector. This is contrary to wave propagation in naturally occurring materials. John Pendry was the first to identify a practical way to make a left-handed metamaterial, a material in which the right-hand rule is not followed. Such a material allows an electromagnetic wave to convey energy against its phase velocity. Pendry's idea was that metallic wires aligned along the direction of propagation could provide negative permittivity. Note, however, that natural materials already displayed negative permittivity. The challenge was achieving negative permeability. In 1999, Pendry demonstrated that a split ring with its axis placed along the direction of wave propagation could do so. In the same paper, he showed that a periodic array of wires and ring could give rise to a negative refractive index. Pendry also proposed a related negative permeability design, the Swiss roll. In the year 2000, Smith et al. Reported the experimental demonstration of functioning electromagnetic metamaterials by horizontally stacking, periodically, split ring resonators and thin wire structures. Later, A method was provided in 2002 to realize negative index metamaterials using artificial lumped element loaded transmission lines in microstrip technology. In 2003, complex negative refractive index and imaging by flat lens using left-handed metamaterials were demonstrated by the Northeastern University Group. By 2007, research experiments which involved negative refractive index had been conducted by many groups. At microwave frequencies, the first real invisibility cloak was realized in 2006. However, only a very small object was imperfectly hidden. Electromagnetic metamaterials. An electromagnetic metamaterial affects electromagnetic waves incident on it via structural features that are smaller than the wavelength of the respective electromagnetic wave. To behave as a homogeneous material accurately described by an effective refractive index, its features must be much smaller than the wavelength. For microwave radiation, the cells need to be on the order of several millimeters. Microwave frequency metamaterials are usually constructed as arrays of electrically conductive elements that have suitable inductive and capacitive characteristics. One type of a microwave metamaterial is a split-ring resonator. Photonic metamaterials, at the scale of nanometers, are being studied in order to manipulate light at optical frequencies. To date, subwavelength structures have shown only a few questionable results at visible wavelengths. Photonic crystals and frequency-selective surfaces such as diffraction gratings, dielectric mirrors, and optical coatings exhibit similarities to subwavelength structured metamaterials. However, these are usually considered distinct from subwavelength structures, as their features are structured for the wavelength at which they function, and thus cannot be approximated as a homogeneous material. However, material structures such as photonic crystals are effective in the visible light spectrum. The middle of the visible spectrum has a wavelength of approximately 560 nm. The photonic crystal structures are generally half this size or smaller, that is less than 280 nm. Plasmonic metamaterials utilize surface plasmons, which are packets of electrical charges that collectively oscillate at the surfaces of metals at optical frequencies. Frequency-selective surfaces can exhibit subwavelength characteristics and are known variously as artificial magnetic conductors or high-impedance surfaces. FSS display inductive and capacitive characteristics that are directly related to their subwavelength structure. Negative refractive index in metamaterials. Almost all materials encountered in optics, such as glass or water, have positive values for both permittivity a micron and permeability a micron. However, metals such as silver and gold have negative permittivity at shorter wavelengths. A material such as a surface plasmon that has either I micron or a micron negative is often opaque to electromagnetic radiation. However, anisotropic materials with only negative permittivity can produce negative refraction due to chirality. Although the optical properties of a transparent material are fully specified by the parameters a micron R and a micron R, refractive index N is often used in practice, which can be determined from all known non-metamaterial transparent materials possess positive I micron R and a micron R. By convention the positive square root is used for N. However, some engineered metamaterials have I micron are less than 0 and a micron are less than 0. Because the product I micron R micron R is positive, N is real. Under such circumstances, it is necessary to take the negative square root for N. The foregoing considerations are simplistic for actual materials, which must have complex valued I micron R and a micron R. The real parts of both I micron R and a micron R do not have to be negative for a passive material to display negative refraction. Metamaterials with negative N have numerous interesting properties, Snell's law, but as N2 is negative, the rays will be refracted on the same side of the normal on entering the material. Cherenkov radiation points the other way. The time-averaged Poynting vector is antiparallel to phase velocity. However, for waves to propagate, AA-a micron must be paired with AA-I micron in order to satisfy the wave number dependence on the material parameters. For plane waves propagating in electromagnetic metamaterials, the electric field, magnetic field and wave vector follow a left-hand rule. This is a reversal of direction when compared to the behavior of conventional optical materials. Negative refractive index is an important characteristic in metamaterial design and fabrication. As reverse refraction media, these occur when both permittivity omicron and permeability omicron are negative. Furthermore, this condition occurs mathematically from the vector triplet E, H and K. In ordinary materials solid, liquid, or gas, transparent or opaque, conductor or insulator the conventional refractive index dominates. This means that permittivity and permeability are both positive, resulting in an ordinary index of refraction. However, metamaterials have the capability to exhibit a state where both permittivity and permeability are negative, resulting in an extraordinary index of negative refraction. Classification: electromagnetic metamaterials divide into different classes, as follows: negative index. In negative index metamaterials, both permittivity and permeability are negative, resulting in a negative index of refraction. These are also known as double negative metamaterials or double negative materials. Other terms for NIMs include left-handed media, media with a negative refractive index, and backward wave media. In optical materials, if both permittivity omicron and permeability omicron are positive, wave propagation travels in the forward direction. If both imicron and omicron are negative, a backward wave is produced. If imicron and omicron have different polarities, waves do not propagate. Mathematically, quadrant 2 and quadrant 4 have coordinates in a coordinate plane where imicron is the horizontal axis, and omicron is the vertical axis. To date, materials exhibiting a negative index of refraction have only been demonstrated as artificially constructed materials. Single negative metamaterials have either negative relative permittivity or negative relative permeability, but not both. They act as metamaterials in combination with a different, complementary SNG, jointly acting as a DNG. Epsilon negative media display a negative imicron R while omicron R is positive. Many plasmas exhibit this characteristic. For example, noble metals such as gold or silver will exhibit this characteristic in the infrared and visible spectrums. Mu-negative media display a positive imicron R while omicron R is negative. Gyrotropic or gyromagnetic materials exhibit this characteristic. A gyrotropic material is one that has been altered by the presence of a quasistatic magnetic field, enabling a magneto-optic effect. A magneto-optic effect is a phenomenon in which an electromagnetic wave propagates through such a medium. In such a material, left and right rotating elliptical polarizations can propagate at different speeds. When light is transmitted through a layer of magneto-optic material, the result is called the Faraday effect. The polarization plane can be rotated, forming a Faraday rotator. The results of such a reflection are known as the magneto-optic Kerr effect. Two gyrotropic materials with reversed rotation directions of the two principal polarizations are called optical isomers. Joining a slab of N material and slab of MnG material resulted in properties such as resonances, anomalous tunneling, transparency, and zero reflection. Like negative index materials, SNGs are innately dispersive, so their imicron R, omicron R and refraction index N, alter with changes in frequency. Electromagnetic band gap. Electromagnetic band gap metamaterials control light propagation. This is accomplished either with photonic crystals or left-handed materials. PCs can prohibit light propagation altogether. Both classes can allow light to propagate in specific, design directions, and both can be designed with band gaps at desired frequencies. The period size of EBGs is an appreciable amount of the wavelength, creating constructive and destructive interference. PC are distinguished from sub-wavelength structures, such as tunable metamaterials, because the PC derives its properties from its band gap characteristics. PCs are sized to match the wavelength of light, versus other metamaterials that operate as a sub-wavelength structure. Furthermore, photonic crystals function by diffracting light. In contrast, a permittivity and permeability define each metamaterial, which is derived from its subwavelength structure and does not use diffraction. PCs have periodic inclusions that inhibit wave propagation due to the inclusion's destructive interference from scattering. The photonic bandgap property of PCs makes them the electromagnetic analog of electronic semiconductor crystals. EBGs have the goal of creating high-quality, low-loss, periodic, dielectric structures. An EBG affects photons in the same way semiconductor materials affect electrons. PCs are the perfect bandgap material, because they allow no light propagation. Each unit of the prescribed periodic structure acts like one atom, albeit of a much larger size. EBGs are designed to prevent the propagation of an allocated bandwidth of frequencies, for certain arrival angles and polarizations. Various geometries and structures have been proposed to fabricate EBG's special properties. In practice, it is impossible to build a flawless EBG device. EBGs have been manufactured for frequencies ranging from a few gigahertz up to a few terahertz, radio, microwave and mid-infrared frequency regions. EBG application developments include a transmission line, wood piles made of square dielectric bars, and several different types of low-gain antennas. Double positive mediums do occur in nature, such as naturally occurring dielectrics. Permittivity and magnetic permeability are both positive and wave propagation is in the forward direction. Artificial materials have been fabricated which combine DPS, ENG and MNG properties. Biisotropic and bianisotropic, categorizing metamaterials into double or single negative, or double positive, normally assumes that the metamaterial has independent electric and magnetic responses described by I micron and A micron. However, in many cases, the electric field causes magnetic polarization, while the magnetic field induces electrical polarization, known as magnetoelectric coupling. Such media are denoted as biisotropic. Media that exhibit magnetoelectric coupling and that are also anisotropic, are referred to as bianisotropic. 4 material parameters are intrinsic to magnetoelectric coupling of biisotropic media. They are the electric and magnetic field strengths, and electric and magnetic flux densities. These 4 material parameters are I micron, A micron, I and I or permittivity, permeability, strength of chirality, and the T-legend parameter respectively. In this type of media, the material parameters do not vary with changes along a rotated coordinate system of measurements. In this sense they are invariant or scalar. The intrinsic magnetoelectric parameters, I and I, affect the phase of the wave. The effect of the chirality parameter is to split the refractive index. In isotropic media this results in wave propagation only if I micron and A micron have the same sign. In biisotropic media with I assumed to be 0, and I a non-zero value, different results appear. Both a backward wave and a forward wave can occur. Alternatively, 2 forward waves or 2 backward waves can occur, depending on the strength of the chirality parameter. Chiral metamaterials are constructed from chiral in which the effective parameter K is non-zero. This is a potential source of confusion as the metamaterial literature includes 2 conflicting uses of the terms left and right-handed. The first refers to one of the 2 circularly polarized waves that are the propagating modes in chiral media. The second relates to the triplet of electric field, magnetic field and Poynting vector that arise in negative refractive index media, which in most cases are not chiral. Wave propagation properties in chiral metamaterials demonstrate that negative refraction can be realized in metamaterials with a strong chirality and positive I micron and I 1/4. This is because the refractive index has distinct values for left and right, given by. It can be seen that a negative index will occur for one polarization if I she micron Ra micron R. In this case, it is not necessary that either or both I micron R and A micron R be negative for backward wave propagation. FSS-based frequency-selective surface-based metamaterials block signals in one waveband and pass those at another waveband. They have become an alternative to fixed-frequency metamaterials. They allow for optional changes of frequencies in a single medium, rather than the restrictive limitations of a fixed frequency response. Other types, elastic, these are a type of metamaterial that uses different parameters to achieve a negative index of refraction in materials that are not electromagnetic. Furthermore, a new design for elastic metamaterials that can behave either as liquids or solids over a limited frequency range may enable new applications based on the control of acoustic, elastic and seismic waves. They are also called mechanical metamaterials. Acoustic. Acoustic metamaterials control, direct and manipulate sound in the form of sonic, infrasonic, or ultrasonic waves in gases, liquids and solids. As with electromagnetic waves, sonic waves can exhibit negative refraction. Control of sound waves is mostly accomplished through the bulk modulus I², mass density I, and chirality. The bulk modulus and density are analogues of permittivity and permeability in electromagnetic metamaterials. Related to this is the mechanics of sound wave propagation in a lattice structure. Also, materials have mass and intrinsic degrees of stiffness. Together, these form a resonance system, and the mechanical resonance may be excited by appropriate sonic frequencies. Nonlinear metamaterials may also be fabricated, which include some form of nonlinear media, whose properties change with the power of the incident wave. Nonlinear media are essential for nonlinear optics. Most optical materials have a relatively weak response, meaning that their properties change by only a small amount for large changes in the intensity of the electromagnetic field. The local electromagnetic fields of the inclusions in a nonlinear metamaterials can be much larger than the average value of the field. In addition, exotic properties such as a negative refractive index create opportunities to tailor the phase matching conditions, which must be satisfied in any nonlinear optical structure. Frequency bands, terahertz. Terahertz metamaterials interact at terahertz frequencies, usually defined as 0.1 to 10 Thz. Terahertz radiation lies at the far end of the infrared band, just after the end of the microwave band. This corresponds to millimeter and submillimeter wavelength Hs between the 3 ohm and 0.03 ohm. Photonic. Photonic metamaterial interact with optical frequencies. The subwavelength period distinguishes them from photonic band gap structures. Tunable. Tunable metamaterials allow arbitrary adjustments to frequency changes in the refractive index. A tunable metamaterial encompasses the development of expanding beyond the bandwidth limitations in left-handed materials by constructing various types of metamaterials. Plasmonic. Plasmonic metamaterials exploit surface plasmons, which are produced from the interaction of light with metal dielectrics. Under specific conditions, the incident light couples with the surface plasmons to create self-sustaining, propagating electromagnetic waves known as surface plasmon polaritons. Applications. Metamaterials are under consideration for many applications. Metamaterial antennas are commercially available. In 2007, one researcher stated that for metamaterial applications to be realized, energy loss must be reduced, materials must be extended into three-dimensional isotropic materials, and production techniques must be industrialized. Antennas. Metamaterial antennas are a class of antennas that use metamaterials to improve performance. Demonstrations have shown that metamaterials could enhance an antenna's radiated power. Materials that can attain negative permeability allow for properties such as an electrically small antenna size, high directivity and tunable operational frequency. Absorber. A metamaterial absorber manipulates the loss components of metamaterials' permittivity and magnetic permeability, to absorb large amounts of electromagnetic radiation. For example, this is a useful feature for solar photovoltaic applications. Loss components are often noted in applications of negative refractive index or transformation optics, but often not utilized in these applications. Superlens. A superlens uses metamaterials to achieve resolution beyond the diffraction limit. The diffraction limit is inherent in conventional optical devices or lenses. Cloaking devices. Metamaterials are a potential basis for a practical cloaking device. The proof of principle was demonstrated on October 19, 2006. No practical cloak exists. Seismic protection. Seismic metamaterials counteract the adverse effects of seismic waves on man-made structures. Light and sound filtering. Metamaterials textured with nanoscale wrinkles could control sound or light signals, such as changing a material's color or for improving ultrasound resolution. Uses include non-destructive material testing, medical diagnostics and sound suppression. The materials can be made through a high-precision, multi-layer deposition process. The thickness of each layer can be controlled within a fraction of a wavelength. The material is then compressed, creating precise wrinkles whose spacing can cause scattering of selected frequencies. Theoretical models. The analogy is as follows: all materials are made of atoms, which are dipoles. These dipoles modify the light velocity by a factor n. The ring and wire units play the role of atomic dipoles. The wire acts as a ferroelectric atom, while the ring acts as an inductor L and the open section as a capacitor C. The ring as a whole therefore acts as an LC circuit. When the electromagnetic field passes through the ring, an induced current is created and the generated field is perpendicular to the magnetic field of the light. The magnetic resonance results in a negative permeability. The index is negative as well. Several material models which frequency response in DNGs. One of these is the Lorentz model. This describes electron motion in terms of a driven damped, harmonic oscillator. The Debye relaxation model applies when the acceleration component of the Lorentz mathematical model is small compared to the other components of the equation. The Drude model applies when the restoring force component is negligible and the coupling coefficient is generally the plasma frequency. Other component distinctions call for the use of one of these models, depending on its polarity, or purpose. Three-dimensional composites of metal non-metallic inclusions periodically randomly embedded in a low permittivity matrix are usually modeled by analytical methods including mixing formulas and scattering matrix-based methods. The particle is modeled by either an electric dipole parallel to the electric field or a pair of crossed electric and magnetic dipoles parallel to the electric and magnetic fields, respectively, of the applied M wave. These dipoles are the leading terms in the multipole series. They are the only existing ones for a homogeneous sphere, whose polarizability can be easily obtained from the Mie scattering coefficients. In general, this procedure is known as the point dipole approximation, which is a good approximation for metamaterials consisting of composites of electrically small spheres. Merits of these methods include low calculation cost and mathematical simplicity. Institutional networks. Duke University has initiated an umbrella organization researching metamaterials under the banner Novel Electromagnetic Materials, and became a leading research center. The center is a part of an international team, which includes California Institute of Technology, Harvard University, UCLA, Max Planck Institute of Germany, and the FOM Institute of the Netherlands. 6 other groups are connected to this organization. MURI, the Multidisciplinary University Research Initiative, encompasses dozens of universities and a few government organizations. Participating universities include UC Berkeley, UC Los Angeles, UC San Diego, Massachusetts Institute of Technology, and Imperial College in London, UK. The sponsors are Office of Naval Research and the Defense Advanced Research Project Agency. MURI supports research that intersects more than one traditional science and engineering discipline to accelerate both research and translation to applications. As of 2009, 69 academic institutions were expected to participate in 41 research efforts. Metamorphose, the Virtual Institute for Artificial Electromagnetic Materials and Metamaterials Metamorphose 6 AISBLA is an international association to promote artificial electromagnetic materials and metamaterials. It organizes scientific conferences, supports specialized journals, creates and manages research programs, provides training programs and technology transfer to European industry. See also, artificial dielectrics are macroscopic analogues of naturally occurring dielectrics that came into use with the radar microwave technologies developed between the 1940s and 1970s. Split-ring resonator delivers strong magnetic coupling for metamaterials. Metatoire composed of superwavelength structures, such as small arrays of prisms and lenses, and can operate over a broad band of frequencies. Magnonics. Academic journals. Metamaterials. Metamaterials books. Metamaterials Handbook, Metamaterials, Physics and Engineering Explorations, References. External links. Educational pages on metamaterials. MLab. Professor Raymond C. Rumpf, Nanophotonics Group. Professor Minkyu. Royal Institute of Technology. Sweden. ETA Research Group. Professor Christoph Kallers. Polytechnique Montreux. Copyright AL. Metamaterials. Electromagnetics Group. George L. Theories. University of Toronto. The INTA Group. NADA INTA. University of Pennsylvania. Electromagnetic Metamaterials. Fraunhofer FHR. Germany. Antennas Research Group. Professor Yang Hao. University of London. INANO Group. Professor M. Saif Islam. UC Davis. Mediums with negative phase velocity. Professor Akhilesh Loktakia. Penn State University. Condensed Matter Theory Group. Sir John Pendry. Imperial College. London. Computational Nanomaterials Group. Victor Podolsky. UMass Lowell. SHVETS Research Group, University of Texas at Austin. US, David Smith's Research Group. Duke University. US, Costas Souklis at IESL, Greece. Photonic, Phononic and Metamaterials Group, Srinivas Sridhar's Group. Northeastern University, Irina Veretennikov's Research Group, Vrij Universiteit Brussels. Belgium, Christophe Crayu's Research Group. Belgium, Martin Wegener's Metamaterials Group. Universität Karlsruhe Karlsruhe. Germany, Giorgio Zouganias's Metamaterials Group. NIT. Japan, Xiang Zhang's Group. UC Berkeley. US, Sergei Chtyakov's Group. Aalto University, Finland, Zheng Kaihu's Group. Beijing Institute of Technology, Institute of Applied Physical Problems. BSU. Belarus, Center for Photonic Metamaterials, University of Southampton. Internet portals. Scholar Google profile on metamaterials, metamaterials.net web group, Center for Metamaterials and Integrated Plasmonics, Duke University, Journal Metamaterials published by Elsevier, online articles, Metamaterials in Science Direct, RSS feed for metamaterials articles published in physical review journals, Virtual Institute for Artificial Electromagnetic Materials and Metamaterials, European Network of Excellence. Metamorphose on Metamaterials, Sensormetrics formed with a specific directive to exploit the recent advances in electromagnetic metamaterials, Metamaterials collection on IAP Science. More articles and presentations. Metamaterials, Homogenization and Parameter Retrieval, Subwavelength Gratings, Dr. Sebastian Guerno. Research on Metamaterials and Photonic Crystal Fibers, UWB Tunable Delay System, Professor Christophe Kallers, École Polytechnique, Montreal. What are metamaterials? An index page by Dr. Stefan Linden and Professor Dr. Martin Wegener, Raytracing Metamaterials, Multifunctionality. Cloaking Devices, Nihility Bandgap, LF Magnetic Enhancement, Perfectradome NIT Japan, Left-Handed Flat Lens HFSS Tutorial Electromagnetism Tutorial, Journal of Optics February 2005 Special Issue on Metamaterials, Experimental Verification of a Negative Index of Refraction, How to Make an Object Invisible, Metamaterials Hold Key to Cloak of Invisibility.